On this video, we will talk about the area formulas for triangles and quadrilaterals. So let's get started. Let's start by discussing the parallelogram. We'll recall that a parallelogram, it's a quadrilateral where opposite sides, which in this case, the top and the bottom, are going to be parallel to each other, and the left and the right are going to be parallel to each other. So remember, this is just a definition of a parallelogram. But now we want to start finding the area of such figure. And the way that we're going to be defining the area of a parallelogram is by just identifying the base and the height, and the multiplication of those two is what's going to be defined as the area of the parallelogram. So for any parallelogram, the area, it's always going to be the base, which is always going to be the lower hand side of the parallelogram, and the height. And now, when we talk about height, we always want to think about a line that is perpendicular to the base. Because the first misconception that some students do is uh, you might think that the left hand side or the left and the right is what's going to be defined as a height, but the height needs to be a line that is perpendicular to the base. And whatever the height is, if I multiply by the base, that's what's going to be defined as the area of the parallelogram. And why is it that the area is being defined as the base times the height? Well, in the future, we're going to be seeing something that is called the Cavalier's principle, and I'd rather wait until the lesson of Cavalier's principle to define the base of the parallelogram. But for right now, let's just define it like this. Base times the height is the parallelogram, but why is it that this works out? Just wait until we start discussing the Cavalier's principle. But let's do one example where we can actually start defining the area of a parallelogram. And we can see that in example 1. So notice like here, we've been given a parallelogram, and here's the parallelogram. Now we want to define the area of this parallelogram. And again, the area, it's always been defined as the base times the height. But at least the base, it's easy to identify because we can see that this is my base, because this is just the bottom part of my parallelogram. So in this case, my base has a value of 10. And now my height is not going to be 8, because remember that the height needs to be aligned perpendicular to the base. And this side, who has a length of 8, is definitely not perpendicular. But we can see that we have this line right here. And notice that this line is perpendicular to the base because we do have the 90-degree triangle here. So now we can think of this line as being the height. But now one thing to notice is that if this line is perpendicular to the base, then definitely this is 90 degrees as well. And now the way that we can define the height, we can see that we have a right triangle right here. This is a right triangle. And if it is a right triangle, then we can definitely use the Pythagorean theorem to find the height. So to find the height, we're going to get, by mistake, we cannot use the Pythagorean theorem here, because notice that here, if we break down the triangle that we do have here, this is 90 degrees, this is 45, this is h, and this is 8. Notice that we're missing the length of this side. If we were to know this length, we can definitely use the Pythagorean theorem, but we don't have it because 10 is not for this side. 10 is for the whole base. So since we're missing the third side, then definitely we cannot use the Pythagorean theorem. But notice that this is one of those special right triangles. This will be a 45, 45, 90 triangle. So here we have two ways that we can define it. I'm just going to be using SOHCAHTOA. So recall that we have those ratios of sine, cosine, and tangent. And I notice that if I make 45 my reference angle, then notice that h, now this is my opposite. And I notice that 8 is my hypotenuse. So now notice that I have a right triangle, I want the opposite, and I have the hypotenuse. So according to what we have here, the ratio that we can use that defines opposite and hypotenuse is the sine. Because notice that the way that we have defined before, we have said that the sine of an angle is equal to the opposite over the hypotenuse. And now let's plug in what we know. Then therefore, the sine of my reference angle, which is 45, is equal to the opposite, which in this case, my opposite is h, over my hypotenuse, which in this case, the hypotenuse is 8. And if I multiply 8 to both sides, that way this cancels out. Now I have an expression for my height. Now the height is 8 times the sine of 45 degrees. Now we know that the height is equivalent to 8 times, and if we use our graphing calculator, you can see that sine of 45 is 0.7071, and if I multiply 0.771 times 8, this is going to give me a value of 5.66. So now notice that I know my base to be 10, and now I also know that my height is equivalent to 5.66. So therefore, I have enough information for me to find the area now, because recall that the area is base times height. I know that my base has a value of 10. I know that my height has a value of 5.66. And if we multiply those two, we should be getting a value of 56.6. Now, this is one of the big misconceptions that students will make, which is we're just going to leave it at 56.6. Well, notice that since we're talking about area, we have to include the units. So let's assume that the length that we're given here, we're given in centimeters. So therefore, the units for our area is going to be 56.6 centimeters squared. Don't forget to always write down the unit for your final result for the area. It's not just going to be 56.6, but since we're talking about area, the area has a unit of a square. Length is first dimension, area is second dimension, so we talk about centimeter squares, kilometer squares. Volume is third dimension, so that's when we use a cube instead of a square. And now notice that we have properly found out the area of this parallelogram. So this is the first figure that we discussed, which is the parallelogram. Now let's discuss the area of the triangle. So I'm aware that you have known, or you know, that the area of a triangle, it's always going to be 1/2 base times height. But why is it that the area for any triangle, it's always going to be defined as this, 1/2 times the base times the height? Well, let's prove that. Let's prove that for any ordinary triangle, for any kind of a triangle, acute, obtuse, regular triangle, equilateral, for any kind of a triangle, the area, it's always going to be defined as 1/2 times the base times the height. So let's prove that this is true. So let's start our proof, which is, well, we have our statement and we have our reason. So let's prove that the area of any triangle is defined as 1/2 times the base times the height. Well, the first thing that we have to write down is the given, and we know that we have some kind of a triangle. XYZ is a triangle. Well, this is my given. And the way that I'm going to think about this triangle is, well, how about if instead of looking at it as a triangle, I'm going to be introducing two auxiliary lines. Let me introduce an auxiliary line that is parallel to y and z, about here. Let's call this point R. And also, let me just make that a better R. So I'm going to be introducing two auxiliary lines, ZR to be parallel to YZ, and also, in addition, I'm going to be introducing this other auxiliary line, XR to be parallel to YZ. So let's just write that down. My second step in this proof is that I'm going to be saying that ZR is going to be parallel to YX, and also YZ is going to be parallel to XR. And all we're doing here is we're introducing auxiliary lines. And now notice what we have said, because if yx is parallel to zr and xr is parallel to yz, then notice that what we have created now is a parallelogram. So now y, x, r, z is a parallelogram. Because this is just a definition of a parallelogram. But we know that we have also created two congruent triangles. Because notice that also one of the properties of a parallelogram is that yz is going to be congruent to yx, and in addition, yz is going to be congruent to zr, and notice that they have this reflected line. YZ is present on both triangles. So we got that this side is congruent to this side is congruent to this side, because these are just properties of parallelograms, and YZ is reflective to each other. So now notice, let's just write that down. We know that YX is congruent to ZR, YZ is congruent to XR, and the reason why that is true is because those are just properties of parallelogram. And now notice that XZ is congruent to ZX, and this is just reflexive, I'm sorry. And now notice that now we can say that YXZ, so triangle YXZ, is definitely congruent to triangle RZ ZX. And now notice that the reason why that is true is because of side congruence theorem. And now we're pretty much done, because now let's just finish up our proof here on the side. So here's my statement, and here's my reason. We're pretty much done at this point, because notice that I know that the area of the parallelogram is equivalent to base times height. This is just definition. But since this parallelogram is the whole unit, but now notice that we were interested in just this triangle that we do have here. But since this triangle XYZ is congruent to triangle XZR, then notice that the area of the triangle that we're looking for, we call it XYZ, or the area of this triangle, is equivalent to 1/2 of the area of the parallelogram. The reason why is because we have two congruent triangles. XYZ congruent to RCX. And now, since the area of this triangle is half of the parallelogram, then now we can finally state that the area of the triangle XYZ is equivalent to 1/2 of the base times height, because the area of the parallelogram is base times height. So therefore, the area of the triangle is 1/2 times the base times the height. And this is, we can just call it substitution. So notice that we can say this for any triangle. For any triangle, we can just construct a parallelogram. We know that the area of the parallelogram is base times height. So therefore, the area of the triangle is half of the area of the parallelogram. So therefore, the area of the triangle is 1/2 times the base times the height. Now I'm going to let you try example 2 and example 3, since these are just area of triangles, which is something that perhaps you have seen on your previous classes. So I'm going to let you discuss that with each other. The last figure that I do want to discuss is the rhombus. And the way that we're going to be defining the area of the area of a rhombus, we're going to define it as 1/2 times d1 times d2, where d1 refers to the first diagonal of the rhombus, and d2 refers to the second diagonal of the rhombus. So what this is saying is that if you have a rhombus and you know the length of two diagonals, then you definitely know the area of the rhombus, because the area of the rhombus is 1/2 times one diagonal times the second diagonal. But why is it that the area of the rhombus is being defined this way? Let's prove it. Let's show that this is true. Let's show that the area of the rhombus, it is actually 1/2 times diagonal 1 times diagonal 2. So let's show that. So let's start by doing a statement and reason. Let's start by writing down the given. What we know is that we have a figure ABCD, which is a rhombus with diagonals D1 and D2. So this is all we know. So we have a rhombus whose diagonals is D1 and D2. Let me actually erase what we have here, because we're going to need this figure to build down the proof. And recall that by definition of a rhombus, then a rhombus is a parallelogram, or it is, and it's not well, I guess it is a parallelogram. It's a parallelogram where all sides are equal to each other, or they are congruent to each other. So therefore, if I concentrate on this triangle and this triangle, notice that now I can say that those two triangles are congruent to each other. We're going to have side, 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 side. So notice that we have two congruent triangles now. Now I can say that triangle ADB is congruent to triangle CDV. And the reason why is because of side, side, side congruence theorem. So now that we have two congruent triangles, notice that also one of the properties of a rhombus is that for any rhombus, the diagonals are always going to be intersecting perpendicular. Therefore, we can say that the line segment AC is definitely perpendicular to DB. And this is just the definition, or I shouldn't call it definition, it's more of a property. So remember that this is just a property of a rhombus. And now we just concentrate on the triangle that is written in yellow. Notice that here we have a triangle where the base of this triangle, is defined as D1. But now, how can we define the height? Because now notice that this is a right triangle, so therefore this line can represent the height. Well, since these two triangles were congruent to each other, and line segment AC was defined as D2, so therefore this segment right here, from here to here, this will be exactly 1/2 of D2. So therefore, the area the area of the triangle DAB, that's going to be defined as 1 half times the base, where the base is D1, times the height, where the height is 1 half of the base of D2. And I notice that if we multiply all this, this is going to be equivalent to 1 quarter D1, D2. Let me just make sure I write this better. So 1 quarter D1 times D2, because this is just the area of triangle. You can call that a formula. So notice that this expression, 1 quarter D1 times D2, that's only going to give me the triangle of the yellow. But notice that since the yellow it's equivalent to the green, then therefore, if I add those two triangles, I must be getting the area of the whole rhombus. So therefore, now the area of rhombus, it is going to be equivalent to 2 times what we got here. Which is just, if we multiply or we simplify this, this is just going to be equivalent to 1 half D1, D2. And notice that all we have done, we have properly defined the area of this rhombus. And again, what we did here is we said, look, I know the area of the red triangle, which is 1 quarter D1 times D2. If I want to find the area of the whole rhombus, that's 2 times the area of the yellow, which is what we did here. And that just simplifies to 1 half D1 times D2, which is exactly how we have defined the area of the rhombus previously. Let's just do one quick example for the area of the rhombus. Let's just do example 5, and then we'll finish the lesson with this. So notice that here we have a rhombus, and we want to find the area of it.